Hello everyone, myself Dr. Vijayakumar, Associate Professor, Department of EC, Aditya University. So in this session we will be seeing LTI systems, LTI system definition, what is meant by LTI system, and also we will be seeing the temporal characteristics of LTI system like mean value of LTI system, how to compute the mean value of an LTI system, how to compute the mean square value of an LTI system, how to compute the correlation functions for an LTI system. So, which will be helpful in computing the output response of the system. At the end of this particular session, students will be able to learn the learning outcome 1, the definition of LTI system, and learning outcome 2, computing the response of the LTI system. Okay, learning outcome 1 and learning outcome 2, definition and how to compute the output response or temporal characteristics for LTI system. So, first we will be seeing what is meant by a system. So, we need to define what is meant by system. System is nothing but a physical device which performs an operation on an input signal and it will generate an output signal. So, it will simply generate a processed output signal. So, for example, let us take an amplifier or filter, dashboard systems. Amplifier, you give an input signal, the amplifier does amplification. So, definitely the output signal is an amplified version of input signal. Filter, we know the filter which will filter out some frequencies. When it comes to low pass filter, you give a random signal, it will allow only low frequency band and stops the high frequency band of signals. So, simply filter will filter out the frequency components, mass spring system, dashboard system, so many systems. Any system which will process the input signal and generate an output signal, we call it as a system. Next, coming to the definition of linear system. So, a system is said to be linear if it follows the principle of superposition principle. Superposition principle consists of again two components. For example, if you multiply the input with A, output also gets multiplied with A, then we call it as homogeneity property or scaling property. Next, if you give the sum of two inputs, if the outputs are also sum of two outputs, this we call it as additivity property. If both properties are satisfied, then we call it as linear system. So, a system is said to be linear simply when weighted sum of input signal is given to a system, it will generate the weighted sum of outputs for the given individual input signals. That is nothing but linear system. Next, a system is said to be time invariant system. For example, if input is delayed by t seconds, output also delayed by t seconds. So, equal amount of delay is applied in the output, then we call it as time invariant system. Otherwise, for example, if you give the delay of 2 seconds, output is delayed by some 4 seconds, the delays are disproportionate, both are dissimilar, then we can say it as time variant system. So, at any point of time, the response delay must be same, then we call it as time invariant system. The input output characteristic simply does not change with the time, okay. It will remain constant, then we can say it as a time variant invariant system. If both the linearity property and time invariance property is satisfied, we call it as LTI system, linear time invariant system. LTI system is mathematically defined as a system which satisfies the linearity property and time invariance property, we call it as LTI system simply. For a continuous LTI system, how do you compute the output response? The system response describes how it reacts to input signal. See here, y of t can be computed simply as x of t convolution of h of t, where h of t is nothing but system impulse response. So, the output is a convolution of input signal and impulse response, and continuous convolution formula is x of tau h of t minus tau d tau. Tau ranges from minus infinity to plus infinity. If it is a discrete version, simply we will replace tau with k and t with n, tau with k, discrete version. Integration will become summation. This is discrete convolution and this is continuous convolution, this is discrete convolution. Okay, impulse response is nothing but when impulse signal is applied as an input, the output response is generally termed as impulse response. Impulse response is generally denoted with h of t. So, here the basic idea is how do you compute the system response? The system response is convolution of input signal and impulse response. Next, mean value of the system response. This is one statistical parameter we will see, mean value of the system response. How do you compute the mean value? So we know already we have computed the system response. In the previous slide we have seen system response. Now we will see how to compute the mean value. Simply applying expectation E of y of t is equal to E of x of t convolution of h of t is nothing but mean value of the output response. So mu y, it is also denoted as mu y of t, E of y of t. Now let us apply the convolution formula h of tau x of t minus tau. H of tau, expectation I am applying inside, h of tau is a constant I am bringing outside. So Ey expectation of y is equal to h of tau expectation of x of t minus tau. If x of t is a Whitson stationary random process, generally the mean will be constant for a Whitson stationary random process. So then mu y is equal to integration of h of tau mu x. Mu x is constant, mu y is equal to mu x integration of h of tau d tau. So mu x into mu y is equal to, which is equal to h of 0. We know that the Fourier transform h of omega is equal to minus infinity to infinity h of tau e power j omega tau d tau. When omega is equal to 0, h of 0 is equal to minus infinity to infinity h of tau d tau. It is nothing but 0 frequency response. So mu y is equal to mu x into h of 0. H of 0, otherwise it is also called as system DC gain or system frequency response at 0 frequency. This is using the Fourier transform. H of 0 is equal to minus infinity to infinity h of tau d tau, 0 frequency or frequency response at 0 frequency. So mu y is equal to mu x into h of 0, which will be helpful in computing the output mean response for a LTI system. Mu y is equal to mu x into h of 0. Next, another statistical parameter which will be helpful in assessing the LTI system is mean square value. Mean square value is mathematically defined as E of y square of t. E of y square of t is equal to E of y of t whole square. But what is y of t? Convolution of h of t into x of t. I am bringing the limits into one side, h of tau 1 into tau 2, E of x of t minus tau 1, x of t minus tau 2, dt1, d tau 2. Assume it is a Whitson stationary random process. This can be written as Rxx of tau 1 minus tau 2. So the mean square value is double integration h of tau 1, h of tau 2, Rx of tau 1 minus tau 2, d tau 1, d2. Next, one more thing which will be useful, transfer function. X of t is the input, y of t is the output, x of omega is the frequency domain input, y of omega is the frequency domain output, h of t is the system impulse response, h of omega is nothing but transfer function. The transfer function is mathematically related to h of omega is equal to y of omega by x of omega. But we know what is y of omega. Y of omega is Fourier transform of y of t. So the Fourier transform of y of t is y of t into e power minus j omega t. But what is y of t? Convolution of input signal and impulse response. Now I am separating input signal and taking inside h of t minus tau. This is mathematically again equal to h of omega. Y of omega is equal to x of tau, h of omega e power minus j omega tau d tau. Again x of tau into e power minus j omega tau is mathematically equal to x of omega. So y of omega is equal to x of omega into h of omega. So h of omega is nothing but y of omega by x of omega, which is nothing but transfer function. So let us see one problem, how to compute the transfer function. A RL network is given, x of t is the input, y of t is the output. Y of omega by x of omega is h of omega, y of omega is I into r, x of omega is r plus j omega L into I. Now y of omega by x of omega is h of omega 1 by 1 plus j omega L by r. If x of t is e power j omega t, what is y of t? You need to prove y of t is equal to x of t into h of omega. We know the convolution formula. Applying the convolution formula and the function is in terms of tau, e power j omega t I am bringing outside. This is mathematically equal to h of omega, but e power j omega t is mathematically given as x of t. So, y of t is equal to x of t into h of omega, transfer function computation. So, this is one more problem computing the transfer function on RC network. So, in this RC network you can see, assume this as Z2, assume this as impedance 2. H of omega is equal to y of omega by x of omega. What is y of omega? I into Z2. This one x of omega is I into Z1 plus Z2. Z2 is 1 plus j omega C1R, Z1 plus Z2 is 1 plus j omega C1 plus C2. So, this is the transfer function for a RC network. The temporal characteristics of LTI system are system response, mean value of the output response, mean square value, autocorrelation function, cross correlation function. These are the temporal characteristics of LTI system. And we have seen few problems relate how to compute the transfer function, how to compute the mean value, and also we have seen derivations up to mean square value. In a similar manner, autocorrelation function, cross correlation function, if you compute, the mathematical equations will be something like this. So, coming to the summary, so we have seen the definition of LTI system and temporal characteristics. We have seen mean value of the output response, and also we have seen how to compute the transfer function for a given system, and also we have seen mean square value of output response. In the next session, we will be seeing the spectral characteristics of random process. So, in all these sessions, we have seen the temporal characteristics. So, in the next session, we will see the spectral characteristics of random process. Spectral characteristics means we will be analyzing the random process in frequency domain. The parameters we use are power spectral density, auto power spectral density and cross power spectral density, and also we will see the relationship between temporal characteristic parameter, autocorrelation function, and spectral characteristic parameter, power spectral density. We will see the Wiener-Kinchy relation in the next sessions. Thank you.